Okay, this section on linear independence is going to look very familiar because we're just solving problems and doing examples that correspond to examples that we did already with column vectors. And we're going to see that the problems reduce to the same sort of matrix issues that we've seen always. Okay, so we know what linear independence means. Let's go back there and just remind ourselves. So this is linear independence of column vectors. Now notice that there's nothing here that's mentioned that the vectors have to be column vectors. Here we're just mentioning vectors, so we might as well apply the same definition to any type of vectors, not just column vectors. So the definition says a set of vectors is linearly dependent if there is a relation of linear dependence on this set. We know what that means, that you have a linear combination of these vectors summing up to 0. Now if there is no linear dependence relation except for the trivial one where all the constants are 0, then this set is called linearly independent. So we're going to use this very same definition for arbitrary vectors in arbitrary vector spaces. All right, so here's the statement. So you can see that this statement is really exactly the same as the previous statement. If vectors, set of vectors, you take a linear combination. If you can find a linear combination that gives you 0, that's a relation of linear dependence. If all the constants are 0, it's a trivial relation. And here we have this very same definition. If you have a set of vectors, un from V is linearly dependent if there is a non-trivial linear dependence relation. Otherwise, they're called linearly independent. Okay. All right, so let's take a look at an example. So here we have a set of vectors, this one, and this one. And we want to know, are these vectors linearly independent? Okay. It turns out that they're not linearly independent because there is a linear dependence relation. So we want to have a way of coming up with such constants when they exist. Okay, so this 3 times the first polynomial plus 4 times the second polynomial plus minus 1 times the third polynomial gives me the 0 polynomial. How do we come up with things like that 3, 4, and minus 1? Well, let's form a general linear combination of the polynomials involved. Well, here we'll look at a different example. Here's a set of polynomials. Let's form an arbitrary linear combination. So we choose arbitrary constants, alpha 1, alpha 2, alpha 3, and alpha 4. We choose these arbitrary constants. And we want to find these constants such that the sum of these polynomials turns out to be the 0 polynomial. Now if you look at this sum, coefficient by coefficient, well, what's the coefficient of x to the 4th? Here's a contribution, 3 alpha 1. Here's a contribution, minus 3 alpha 2. Here's a contribution, 4. Here's a contribution, 2. So you add up all of these, 4 alpha 3. This one is 2 alpha 4. So you add up all of these 4 contributions, and that's the coefficient of x to the 4th in the linear combination. So the 3 alpha 1 comes from here. The minus 3 alpha 2 comes from here. 4 alpha 3 comes from here. 2 alpha 4 comes from here. That's the coefficient of x to the 4th. We can do that for every coefficient in this linear combination polynomial. Let's just look at, for instance, at the last term, the constant term. This gives me minus 1 alpha 1. That's where I get this term here from. This gives me 2 alpha 2. That's where this term comes from. This one gives me 1 alpha 3. That's where this comes from. And this gives me 1 alpha 4. That's where this comes from. So here, what's written here is the linear combination of all of these written and grouped such that all of the terms of all the coefficients of like powers of x are grouped together. Now, in order for this polynomial to be 0, we need all of these coefficients to be 0, and that's where this comes from. This is the coefficient of x to the 4th, x cubed, x squared. I think there's 2 more equations on the next page. X and the constant coefficient. Okay, so now we have reduced it to a system of linear equations that we're experts in. This is a homogeneous system, so you only need to take the matrix of coefficients. You can reduce it, and you end up with this reduced form. When we try to find the solution alpha 1, alpha 2, alpha 3, alpha 4 from this reduced form, you can see that you read off the equations here. This first row represents alpha 1 equals 0. Second row represents alpha 2 equals 0. Third row represents alpha 3 equals 0. Fourth row represents alpha 4 equals 0. The only way to get a linear combination of these polynomials, that gives me the 0 vector is to set all of the coefficients equal to 0. Only the trivial relation holds. The polynomials are linearly independent. Okay. All right, now this should very much remind you of the same sorts of things that we did with column vectors. It's the same sort of methodology, same sort of idea. It's just that we've turned an equation with polynomials into a system of linear equations and solve for the coefficients. Now we did that for polynomials. You can imagine that we can do this for matrices as well. Set it up exactly the same way. If this set R is linearly independent, that means we can that there's only a trivial solution to the following system. Alpha 1 times the first matrix plus alpha 2 times the second plus alpha 3 times the third plus alpha 4 times the fourth. If there's only a trivial solution to this system, that means that R is linearly independent. Now you just do the same sort of thing. You rearrange this matrix equation into an equation for a big matrix, and if in order for this to be the 0 matrix, in this case the zero quote vector is a matrix because we're dealing with matrices. The only way for this result to be 0 is for every single entry to be 0. We end up with 6 equations. You go ahead and row reduce. Turns out that there's only one solution of all 0. So yes, R is linearly independent. If you do the same thing for the other set of matrices, S, form arbitrary linear combination, write out the resulting matrix, group the terms, set equal to 0. You get a system of linear equations. When you reduce, you get free variables, which means that there are non-trivial solutions for the constants. Okay, so that means that, in fact, S is linearly dependent. Okay, and then once you show it's linearly dependent, then you can give a concrete example by choosing your free variables arbitrarily and constructing the other variables from them. All right, now here's an example in the so-called crazy vector space, which uses different operations. So what this says is, let me go back there. In the crazy vector space, we have this different kind of vector multiplication and addition. So here I've copied the operations of addition and scalar multiplication in this so-called crazy vector space, and we simply need to apply these rules, right? So in order to determine whether or not these vectors are linearly independent in the so-called crazy vector space, we need to see whether or not we can form a relation of linear dependence. So this is a relation of linear dependence. See, this doesn't look any different from what we've done with other vectors. The only difference here is this plus now means crazy vector space plus. It's not just ordinary plus. And this scalar multiplication is crazy vector space multiplication, not ordinary scalar vector multiplication. Okay. Now if you go back to the example, it turns out that the vector -1, -1 represents the 0 vector. Okay. So we can set this up. -1, -1 is equal to 0. Here's our linear combination. Let's do the rules. A1 times the vector 1, 0 is according to this rule here. So I'd have A1 times 1, 0. So that would be, if you work out the rules, this is going to be, let me make sure I've got this right. Okay. Yes, A1 times 1, 0. Let's use the rules here. A1 times 1, 0 is going to be equal to, well, let's plug in. This is going to be A1 times 1, which is 1. I'm sorry, this is not plus 1. This should be -1. Sorry about that. As you can see, I've rewritten my scalar multiplication to be correct this time. Okay, so let me do a1 times 1, 0. So that's going to be alpha times x goes to a1 times 1. And then I have a plus. And then here I have alpha. That's the same as a1, which is a1. And then I have the minus 1, which gives me minus 1. Okay. In this case, I have alpha times y. A1 times y is 0. And then I have plus alpha, so that's plus a1. Then I have minus 1. Okay. So that's alpha 1 times 1, 0. Okay. Let's see if we can. So that's where we get this one from here. To do this one here, I have alpha 2 and 6, so I'm going to have, according to this rule, I'm going to have 6 times alpha 2 plus alpha 2 minus 1. That follows this rule here, alpha x plus alpha minus 1. And then from here, since I have my a2 is alpha, and then 3 is my y, so I'm going to have 3 alpha 2 plus alpha 2 minus 1. And I'm just applying these scalar multiplication rules to these two individual vectors. Okay? This is just simplifying these results. Then from here we do the sum of these two vectors according to this rule. You sum the x components and then you add 1. So 2a minus 1, 2a1 minus 1 plus 7a2 minus 1 plus 1. And then you add the y components, a1 minus 1 plus 4a2 minus 1 plus 1. That gives me this second component. And this gives me my result. Now, in order for this to be a valid linear dependence homogeneous relation, we need to end up with minus 1, minus 1. So that's where these two equations come from. Notice the minus 1's cancel, and I still get a homogeneous system of equations. And you solve it the very same way. So I hope you're getting the feeling that regardless of what type of vectors you have, in order to show linear dependence or independence, you use pretty much the same procedure. All right, so we'll stop there.